Greetings, welcome to W5U4 Instruction for Engineering Design Thinking Part 2. In the earlier unit, we understood some aspects of instruction for engineering design thinking. In this unit, the outcomes are understand some developments in instruction for engineering design thinking, including the use of reverse engineering in such instruction, that is instruction for design thinking, the use of reverse engineering, instruction for parametric design thinking and instruction for generative design thinking. This is basically based on the influence of AI tools. Reverse engineering, in the previous unit we noted that reverse engineering could be used for instruction in engineering design thinking using projects in the early semesters of the engineering programs. Reverse engineering is a powerful method for instructing engineering design by analyzing existing systems. These existing systems could be successful ones working well, or it could be even failed ones. In some cases, even failed systems provide enormous learning experiences to the students. Of course, caution is to be exercised regarding any IPR issues, intellectual property rights, and their violations should not land the institute into trouble. So, those issues must be taken into account, but it is not very difficult to get such systems for educational purposes. It is most commonly used as a part of project based approach to instruction discussed in the earlier units. What are the key features of reverse engineering? System decomposition, first aspect, breaking down a complex system into its subsystems and components. Understanding functional and physical interactions of these decomposed parts or subsystems. Basically, once we decompose, what are the functional and physical interactions among these subsystems? What are the roles of these subsystems? What are the functions of these subsystems or components, and how they interact with each other? The student needs to understand. So, functional identification, determining what each component or circuit does. Then material and manufacturing analysis, understanding how components are selected and used in the construction of the system, which components are used, why those are used, and which kind of manufacturing process, if there is a manufacturing activity involved, which kind of process is adopted and why it was adopted. So, then based on all this, design rational inference, why specific design choices were made, whether it is component selection or layout decisions or manufacturing process selection, whatever it is, why those specific design choices were made. Students have to do some brainstorming, perhaps with the help of instructor, and understand what went through the minds of the designers when they made these specific choices, and are they okay, or do they have, the students have a different idea? Do they find some ways of improving upon those designs? All this can be discussed. So, reverse engineering and instruction for design thinking, it can be used quite effectively in instruction, as we just now mentioned. Students are given an opportunity to work with real world systems. So, this activity can be used to enable the students to bridge the gap between textbook knowledge and industry practices. They understand what is that last mile bridge between a textbook knowledge and getting to a marketable product. Students can be encouraged to engage in critical thinking, as we just now mentioned. Why did the engineers do it this particular way? Why these specific trade-offs in the designs were made, for example, between cost and performance, complexity and reliability, why those specific choices were made. Creative thinking in students can be promoted by asking them to propose, after analyzing the existing designs, improvements in the design. Can the students come out with a better design or alternative designs? Peers can critically examine and discuss these improvements, alternatives. They can even produce a well thought out critique of the existing design. So, these are all the activities which will promote creative thinking in students. We can use even a failed system for reverse engineering, and the students can be trained in failure analysis. Why did the design fail? What are the root cause analysis that can be carried out, and how the future possible failures can be avoided, what changes in design need to be made, what changes in the choices of materials etc. are to be made. All these can be instructed, and the students can be trained in all these aspects. Benefits of use of reverse engineering: there are plenty of benefits. It helps the students in several ways: system level design thinking, integration of theory and practice, real world engineering constraints, creative thinking, failure analysis, design trade-offs, innovation. There are so many ways that the students can benefit from such reverse engineering studies. Next, let us look at parametric design in engineering. This parametric design in engineering focuses on creating designs where a relationship between design elements are defined by parameters. That means, we are able to get a family of designs based on the parameters. So, the relationships are defined by the parameters and rules, allowing for easy modification and exploration of design variations. Of course, in all cases it may not be possible, but where possible, if we can express the relationships through parameters and rules, then we can get a parametric design, and the exploration of design variations becomes relatively simpler. It leverages parameters to define and explore design variations. It allows for more flexible, efficient and optimized design processes, particularly useful when dealing with complex systems. Generally, parametric design is based on software systems for design, and quite often simulation is used by engineers to evaluate the design options. As you vary the parameters, how the design solution space keeps changing, and how the performance and other desirable outputs features can change, can be explored much more easily using simulation. So, parametric design generally goes hand in hand with simulation to make the final design choices. What are the key concepts of parametric design thinking? Parameters as the drivers of the whole process. The entire design process is driven by parameters. So, parameters as the drivers. The parameters could be dimensions, material properties, electrical values, etc. These are the core variables that influence the design. These can be changed systematically to explore design alternatives or optimize the performance. Designs are defined by relationships or equations linking the parameters. Changing one parameter automatically updates dependent elements. This is taken care by the software, the design software itself. So, changing one parameter automatically updates dependent elements, geometry, circuits, simulation outputs, etc. Automation and iteration. So, the whole idea of parametric design is that the models enable automatic updates and rapid iterations. So, one can go through some other tool like simulation to quickly run through several possible iterations and arrive at the entire design space much more quickly, and this is ideal for optimization tasks and sensitivity analysis. And often these tools all get integrated, that is integration with CAD and EDA tools. So, often implemented using software that supports scripting or parametric modeling. One should be able to write a script to run through iterations automatically and plot perhaps the performance. So, these are a lot of automation which is involved in such parametric design thinking ideas. So, one could use tools like MATLAB, Simulink, Spice. Then we come to the generative design thinking in engineering. These were influenced by the recent developments in technology, particularly artificial intelligence, machine learning, AI/ML. These have been dramatically influencing all areas of engineering, and they are influencing the design thinking also quite significantly. So, the traditional design thinking is going through fair number of changes because of the influence of the AI/ML, and of course, in turn the AI/ML usefulness in thinking about designs also is undergoing changes. That is, the influence is reciprocal. That is, developments in design thinking like parametric design, generative design have been influencing the related technologies and tools like deep learning, genetic algorithms, parametric design tools, generative design tools and all. So, AI and ML and the design activities, they have been influencing each other, and together with these theoretical developments like for example, developments in cognitive domain including computational thinking, engineering systems thinking. Earlier they were there, but more recent developments in these areas like computational thinking, engineering system thinking are similarly getting influenced by and in turn are influencing design thinking. So, in a kind of way each is getting influenced by the other and is also influencing the other. So, this scenario is captured in evolving design thinking model proposed in the literature. So, this is the model that researchers are proposing in the literature. This particular figure, the source is Exploring Generative Design Thinking for Engineering Design and Design Education by Xingyang et al. So, you can see there are three layers in fact. One layer is technology layer, genetic algorithms, machine learning, deep learning including standard neural networks, sophisticated deep neural networks and standard architectures. All these go under machine learning and deep learning, parametric design tools, generative design tools, topology optimizations. There are many other technologies which are developing very rapidly. Then at the bottom layer we have the theoretical developments in cognitive theories, computational thinking, engineering system thinking and many other developments. So, in the middle layer we have the evolving design thinking. Traditional design thinking still continues to be there and it is quite useful, but branches are emerging from that. Parametric design thinking already has become quite well established and stable. Now, more recently in the past maybe 5-6 years, generative design thinking also is gaining a lot of importance. So, all these black arrows show evolution and the arrows show the influence. That is, you can see that the technology is influencing evolving design thinking if you see the left side of the figure, but on the right side you can see that the evolving design thinking is also influencing the technology. Same way, evolving design thinking is influencing the theories in cognitive domain and the theories in cognitive domain are influencing the design thinking. So, there is a lot of cross current going on and this is making a lot of changes in the design thinking models. Generative design and parametric design. As noted earlier, parametric design represents a design using parameters which allows the creation of different design options by manipulating those parameters. PD and GD may look similar, but they are distinct and different. PD does not necessarily use AIML algorithms, it can, but does not necessarily use AIML algorithms to automatically generate design options. Even though generative function could be added to PD, but it is not necessarily mandated that PD should use AIML. On the other hand, GD may be able to use PD for design problems, but could be modeled parametrically. That is, if the design problem allows parametric modeling, then GD could use that. Otherwise, GD may not use it. So, you have kind of choices available here. Parametric design thinking has been considered as a continuity and change within the evolution of design thinking. One stage. Key features of generative design thinking in engineering: goal driven design, that is the first thing. Designer specifies the goal. Ultimately, what is it that the design should achieve? What is the goal? Example, certain weight or certain strength or certain material usage is mandated, not how to achieve it. Designer does not specify the specific approach or algorithm to be used in order to realize that specific intended goal, only specifies the goal. Then the system, the process uses computational algorithms and algorithms of AI, artificial intelligence, to generate a wide range of design options quickly. Designer is not specifying any particular design approach. The system, the process picks up the approaches based on AI as well as machine learning. But the designer has to provide the constraints as inputs. So, the designer has to specify, for example, something about the materials, the cost should not exceed so much, or the materials can be only from these types 1, 2, 3. So, whatever are the constraints the designer needs to specify. It could be on materials, it could be on cost, or it could be on performance criteria, the efficiency cannot be less than 95%, whatever. The designer has to think about the problem and specify the constraints as inputs to the model. Obviously, this is highly tool based, this entire approach. So, multiple design alternatives exist. The system generates multiple design options, often with multiple conflicting features. That is also possible. Machine learning allows these kind of things to be developed. A human designer might not even think of many of these design options. There are so many off the box, out of the box, innovative solutions that the ML models can produce, solutions which might not have been thought of even by the designers, human designers. So, quite many surprises are possible when machine learning models are used to generate the solutions. The engineer evaluates these numerous generated design options, makes the trade-off decisions. Notice the final decision is still by the human engineer, and selects the final design, fine tuning it further if required with the assistance of tools. But there are also issues like aesthetics which cannot be still algorithmized that easily. That is, there are issues which are difficult to put in the form of an algorithm for a machine to implement. But the important point is that the human designers still have a key role to play. Iterative learning, the machine has the capacity to learn from the interaction with the human designers. That is, the system improves design outputs based on feedback, often using machine learning models. There are several ML models, all of them can store the decisions made in the current iteration and improve their working. Though GD can be seen as a design automation process, as we mentioned just now, human designers remain critical as in the traditional design process. However, they need different skills and mindsets. So, human design engineers need to specify the goals, necessary design parameters and constraints. How to specify it in a form that the system would need, engineers needs to be trained, design thinkers need to be trained. Make trade-off decisions among numerous generated design options, make aesthetic judgments. Such requirements cannot be easily encoded into algorithms and they largely depend on subjective perspectives of the designers. So, still the human designers have a significant role in such areas. What are the key benefits of such generative design thinking? The first and obvious benefit is that enormous time savings, substantial time savings because of the automated design generations. In many areas of the entire activity, there is a considerable amount of time that is saved. Then innovation, they can produce novel efficient designs. Often human designers might not even be able to conceive of such possibilities, out of box thinking ideas. Customization easily adapts designs to new constraints. If the constraints change regarding any of the features like materials or cost or efficiency, etc., it is very easy to modify the constraint, ask the system to redesign the final activity. So, the system can very easily adapt to these changes in the constraints, because the algorithms are all machine algorithms. Sustainability often results in reduced material usage. The system is able to optimize the material usage much better than what probably a human designer could do, because of the enormous computational power of the machines which are being used for the AI purposes and ML purposes. Instruction for GD thinking in engineering, all the issues that we discussed in the previous unit regarding instruction for design thinking in engineering curricula, they hold good in the present context also, in the sense that complex, open-ended and realistic problems, collaboration, communication, etc. In addition, instruction must focus on constraint-based thinking, how to come out with the constraints in a formal way, in a formal fashion, and provide them as inputs to the model. So, people must be trained in that aspect. Then iterative prototyping, many designs perhaps need some quick prototyping in order to evaluate them further. Then fail forward culture, this also becomes extremely important, we will presently quickly discuss that. AML and generative design tools, many sophisticated tools are becoming available. So, the students need to be trained in these tools. Help the students understand engineering constraints, as we just now mentioned, materials, environment, cost, manufacturing limitations, access issues for troubleshooting. Many issues need to be considered and the students must be trained to consider these issues systematically and formally and specify them in a way that the system can accept and interpret. Use instructional components like fishbone diagrams, causal loop diagrams, trade-off analysis tools, many of these are useful. Iterative prototyping, encourage rapid prototyping, testing and refinement, often this is quite helpful. So, you can use low cost, eco-friendly, reusable materials for rapid prototyping, example cardboard, students when they are working. Then provide suitable tools, provide helpful workplaces when you are designing, when you are brainstorming, when you are working in a group, when you are fabricating, when you are testing. There are multiple places physical spaces where they have to work, and they all must be helpful workplaces, well organized, then ergonomic placement of the tools and lighting and other issues. They all influence the efficiency with which the students are able to work. So, carefully designed workplaces are important. Then you need fail forward culture. Failures can occur for a variety of reasons, including incorrect constraint specifications. Most often that is the reason. The students are not able to specify the constraints properly. Do not disparage the failures. Support students to treat them as learning opportunities rather than as setbacks. If because of incorrect constraint specifications the design is failed, that is fine. Now the students are understanding how not to specify that particular constraint. So, it is all a part of the learning exercise. So, you must encourage the students to explore and experiment and learn from them rather than disparage them. So, encourage analysis, encourage them to analyze their mistakes and learn from them. So, this is a kind of fail forward culture. Of course, in the industry the context is different. There it does cost when a failure occurs, but still many industries do encourage fail forward culture. But we are talking of an educational setting and a student learning. So, obviously the instructors need to have a positive attitude towards the failure of the students. So, provide a very relaxed environment free from grade related stress. Let the students not worry about how this will going to affect their grades and all that. The objective is the students learn. The students learn both from success as well as failures. So, this is a part of the fail forward culture, extremely important. And finally, AI, ML and generative design tools are becoming extremely important, powerful and diverse. So, students from all disciplines, not necessarily computer science or AI, ML students, but students from all disciplines, whether mechanical or civil or electrical or instrumentation or aerospace, students from all disciplines need to be provided a basic introduction. From the user's perspective, we do not have to go into behind the hoods of how those designs work, but they need as a user to be able to understand how the tool functions, how to interact with the tool, how the user interface works. So, they must be trained some basic introduction in computational thinking and the features and uses of AI and ML, provide necessary tutorials on the use of generative design software, for example, Autodesk Fusion 360. There are many other, whatever be the tools or software systems that your institute is using, provide the necessary tutorials. Encourage students to analyze the AI generated and human generated designs and reflect on the relative strengths and limitations. This kind of a thinking will promote the deep learning by the students. Let them compare the AI generated and human generated designs and let them analyze where AI generated solutions are better, where human generated designs score better. So, in summary, we can say of both the units taken together, this unit and the previous unit, design in a major sense is the essence of engineering. Design thinking reflects the complex cognitive process of inquiry and learning that designers engage in while developing solutions. The key principles of design thinking have remained mostly unchanged. Even with the emergence of AI and ML and all, the key principles of design thinking are same. However, technologies including the significantly disruptive ones of AI and ML have been radically influencing the design thinking, which in turn is influencing these technologies. So, it is widely accepted that teaching design thinking is quite difficult. It is becoming much more challenging in the current scenario with the strong influence that AI ML is making on these choices. Teachers need to be alert to these fast paced changes in technologies and technology mediated design process, particularly the disruptive AI ML technologies. Teachers must continually innovate their instructional approaches also in order to remain current and relative in the fast paced scenarios emerging today. And that completes our discussion of instruction in design thinking. In the next unit, we will understand simulation approach to instruction. Thank you. We will meet again in the next unit. Thank you.